So we've done a couple example of Taylor series where the center was 0. Let's try one where the center is some other value of x. By the way, a Taylor series centered at 0, remember, is called a Maclaurin series. So this is just going to be a regular Taylor series. And let's look at the function y equals log of x. And we'll center it at x equals 1. Okay? Now, the reason I'm choosing x equals 1 here is because the log of x isn't even defined at 0. So trying to write down a Taylor series formula centered at 0 isn't going to be an option. We can't even find a value of the function to try to match them up. But at x equals 1, the log of x is a nice smooth function. It looks something like that. So there's the log of x. And so we can certainly find a way of representing that with a series. And our Taylor series formula says that we should be able to write f of x as the sum from n equals 0 to infinity of the nth derivative evaluated at the center point, which in this case I guess will be 1 all over n factorial times x minus the center point raised to the n. And the only thing that's missing to be able to use this formula is a nice pattern for all of those derivatives. Okay, so let's start by writing down f of x equals log x, and we're going to compute its first few derivatives. All right, so f prime of x, derivative of log x is just 1 over x, or we could write that as x to the negative 1. And if I want to take a derivative of that, I will have negative 1 times x to the negative 2, applying our power rule. And if I take a third derivative, I will have to bring down a negative 2. And now my power will be negative 3. And if I take a fourth derivative, we'll have negative 1 times negative 2 times negative 3 times x to the negative 4. And you may notice that there's a nice little pattern there. If I want the nth derivative, well, first of all, the power of x is negative n. And then what do we have out front? Well, we have 3 negative numbers, or when we're doing the fourth derivative. We have 2 negative numbers when we're doing the third derivative, and we have 1 negative number when we're doing the second derivative. And so we can think of that as negative 1 raised to the n minus 1. That would take care of the negative signs. And then what's left is just the product of all of the integers, right? We have 1, then 1 times 2, then 1 times 3. And so that is just a factorial. And in this case, the factorial goes up to 1 less than the exponent. So it'll be an n minus 1 factorial. And let's just quickly check. If I plug in 0, this formula is not going to work because of the log, but for all the other ones, I think it should check out. If we plug in n equals 1, we'll get negative 1 to the 0 power, so positive 1, times 0 factorial, which is 1, times x to the negative 1. That's just x to the negative 1, so that matches with our f prime. And if we plug in n equals 2, we should see something that's consistent with our second one, and it should work for all of the others as well. Okay, so let's plug that into our formula. We have the sum from n equals 0 to infinity. And in fact, since the log of x was sort of a special case, before we do that, we can actually plug in some things. Plug in the value of 1. So let's compute f of 1, f prime of 1, f double prime of 1, f triple prime of 1, and so on. And then we'll plug it in, because I want you to notice what's going on here. So f of 1 is the log of 1. Well, log of 1 is just 0. F prime of 1 is going to be x to the negative 1, which is just 1. The next one will be negative 1. The next one after that will be, notice when you plug in 1 to this exponential, the x to the negative 3, not exponential, this power of x, you'll see that you get 1 every single time. And so really the x to the negative n part is 1, and we'll just be left with the factorial part. So it'll be 2 factorial, and then minus 3 factorial. And in general, we'll have minus 1 to the n minus 1 times n minus 1 factorial. Okay, so there's the pattern of those derivative terms that we need for our series. Now let's plug this general formula in, keeping in mind that the pattern was broken for f1, but since that's 0, we don't really need to include the n equals 0 term, do we? We know that that's ultimately going to cancel out. And so what we'll have is f of x is equal to the sum from n equals 1 to infinity. So we're throwing away the 0 term because we know it's 0, doesn't contribute anything. And then instead of our nth derivative, let's actually write our formula. Negative 1 to the n minus 1 times n minus 1 factorial. So that's the top. That was divided by n factorial times x minus 1 to the n. And we can simplify that even further because notice n factorial is just n times n minus 1 factorial. And so that's going to cancel. And we will have the sum from n equals 1 to infinity of minus 1 to the n minus 1 all over n times x minus 1 to the n. And if we want to start writing out terms, we could plug in some values of n. We'd see that when n is equal to 1, we'll have negative 1 to the 0 all over 1 times x minus 1 to the 1. For n equals 2, we'll have negative 1 to the 1 over 2 times x minus 1 squared. And then we'll have negative 1 squared over 3 times x minus 1 cubed. And we could keep going as long as we want, but there's a nice little pattern there. When you have an even power for the negative 1, we know that's a plus 1. And so this is just x minus 1. The next term will be negative because it's an odd power of negative 1. And so that'll be x minus 1 squared over 2. Then it'll be a plus again, x minus 3 squared, x minus 1 squared, x minus 1 cubed all over 3. We'll see if we can say that correctly. And the pattern should continue, x minus 1 to the 4th over 4. And it's just alternating from positive to negative for each term. Okay? All right, so there's our series. We could look for the radius and interval of convergence, but we've done enough of those that I think I'm going to skip that. But let's actually look at a graph of this function. All right, so I'm going to go back to my Taylor series calculator. I'll graph the log of x. And our series we found, I'll plug in our formula. It was, we had negative 1 raised to the n minus 1 over n times x minus 1 to the n. And we start with n equals 1 rather than 0. And we'll zoom in just a little bit to see that better. Okay, with one term in our sequence, well, if we just use 0 terms, then we have a horizontal line that matches the value of the function only. If we add one term, now we're going to match the value of the function and the slope, and so we have a tangent line. And as we add up more terms, we should see that this does better and better and better. All right, so there's 89 terms, and if I show 100, we'll take a minute to do the calculation, and it looks like it's hugging the log of x very tightly over this range, but it looks like around x equals 2, it breaks down, and then of course it doesn't match the function for negative values of x. It only works from 0 to 2, and that's because the log of x isn't even defined for negative values of x. And so based on that picture, that suggests that the radius of convergence is 1, and the interval is from 0 to 2. Okay, so there is a Taylor series not centered at 0, but rather centered at 1, and it gives us a way of calculating the log of x. All right, let me just show you one more thing before we move on from this example. There is another way of getting to the same conclusion, and that is to go back to our geometric series. 1 over 1 minus x is equal to the sum of x to the n. All right, well, let's plug in. Let's replace x with, how about x minus 1? Let's plug that in for x. Or if you want to call it y minus 1, we can do that, and we'll just rename it later on. So let's say x equals y minus 1. What would that give us? 1 over 1 minus y minus 1 is equal to the log of, oops, let's make it, how about 1 minus y? That looks a little better. That's going to give us the log of 1 over y. Okay, and so if I plug that in on the right-hand side, that should be equal to the sum from n equals 0 to infinity of 1 minus y to the n. Or you could factor out a -1, and write it as minus 1 to the n times y minus 1 to the n. And so that would give you a power series for the function 1 over y. And if we want to then compute the log of y, we could integrate that. Log of y is the integral of 1 over y dy. And so if I integrate this series term by term, that should give me a power series for log of y. And remember, we can only integrate term by term where the series is convergent. And this one is going to be convergent between 0 and 2. So let's do that. We'll have -1 to the n. Well, that's constant. It does not depend on y at all. So we'll just integrate this last piece. And that is a power. So when you take an antiderivative of power, you increase the power by 1 and divide by the constant. But there is one value of n where that doesn't work. Well, no, actually, no, it's fine. We're fine. -1 to the n times y minus 1 to the n plus 1 over n plus 1. So there's our antiderivative. And now, notice this is a little different than what we had before, but that's because our sum starts with n equals 0. Let's start our sum with n equals 1. Well, if I start with 1, and I want the exponent of -1 to be the same, this needs to now be an n minus 1. And if I start with 1, now I only need to start the exponents with n to get a first power for my first term. And the same thing is true with the denominator. The n plus 1s can be now written as n, and we'll still get the same terms in our series. And notice that is precisely what we derived up above, only written in terms of y. Okay? So sometimes there are a couple of different ways of getting at these series problems. One is taking the geometric series, applying some substitutions, some derivatives, or some antiderivatives to derive, to turn the 1 over 1 minus x into the function we're actually interested in, and using that approach. Alternatively, we can apply the Taylor series formula and compute our Taylor series by finding a bunch of derivatives, identifying the pattern, and then plugging in.